Swayam Prabha. Digital India. Educated India.
Okay, so we continue our discussion on nonlinear dynamics, and in the previous lecture we had a look into the theory of higher order dynamical systems. So, now what we will do is for the next few days we would be focusing on various applications, where we would see how the theory developed or rather studied by us for nonlinear dynamical systems of higher order can be used for the analysis of systems which are of relevance to process engineering as well as to natural sciences. So, today we will take one particular example of reactor stability analysis. Okay. So, let us have a look into the system that we have in front of us. We had this example right in the first lecture, where we saw that we have the case of transient operation of a jacketed CSTR. CSTR stands for continuous stirred tank reactor. We gave two model equations, dC by dt is equal to F by V C F minus C C minus R, and dt by dt is equal to F by V T F minus T plus minus of delta H rho upon C P times R minus U A upon V rho C P T minus T J. Various quantities have been elaborated below. And we saw that this is a dynamical system, because the concentration of a species inside the reactor changes with time when you are doing a transient operation, and so does the temperature of the reactor. We would see today that there are various forcing functions which act upon the system. The flow rate of the reactants, for example, is a forcing function. The temperature of the jacket can act as a forcing function, and so on. So, we will see how does the dynamics of the system behave in this particular case, when we can see that this particular set of equations are in fact nonlinear equations. When we plug in the rate expression in this particular equation, then we will see that the system is highly nonlinear, and then we will try to understand the dynamics, especially the dynamics around the steady state. So, before we go into the details, let us first try to understand what the system is really about, what are the various assumptions under which these particular equations would remain true, and what are the assumptions and approximations under which we can do the dynamical analysis, and if that be the case, the dynamical analysis would be true for certain ranges of the parameters of the system, and what are those ranges under which we can expect the analysis to hold true. So, let us have a look into this particular system. So, what we have is a CSTR. So, it is a tank which is equipped with a stirrer, so that it is assumed that there is a complete mixing of the contents inside the reactor. Okay. It is a continuous mode of operation. So, there would be an inlet flow. So, let us say that the flow of material in comes at a volumetric flow rate F in. Okay. So, F in is the volumetric flow rate of the material which is coming in. In the inlet, the concentration of the species is maintained as C F. F stands for feed. So, the concentration of the species in the feed, and then what will also be there is that there would be a corresponding temperature of the inlet stream, and that would be denoted as T f. Fine. The material would also be continuously flowing out. So, I have an outlet stream, and before I can write anything about the outlet stream, let me first try to understand what goes on inside the reactor. So, the material flows in with certain concentration of the species, and let us say that an irreversible reaction A going to B takes place inside the reactor. Okay, we have assumed that the reaction is irreversible, and we are tracing only the concentration of A. If you know the temporal profile of concentration of A, then you would automatically know the temporal variation of B using this simple reaction equation. So, C everywhere in our notation simply refers to the concentration of the species A. So, now once the species enters into the reactor, the reaction takes place, and that well mixed contents have the concentration C. So, concentration of A inside the reactor is simply denoted by C. There are no spatial variations inside the reactor. This is an assumption, okay, that there are no spatial variations inside the reactor, and since there are no spatial variations in concentration, the system is well mixed. You can as well assume that there is a constant temperature T inside the reactor. Okay. And since the contents of the reactor are simply flowing out from the outlet stream, you can say that the contents here at the outlet also have the concentration C. They are at temperature T, but the flow rate may be different. At this point of time, we may not say anything about the flow rate. So, therefore, the volumetric flow rate is C F out. Okay. So, the volumetric flow rate is C F out. Now, inside the reactor, the reaction mixture will have some volume, and let us denote that volume by V. And the intrinsic reaction rate for this system is denoted by R. Okay. Now, if we assume, so if we assume a first order irreversible reaction taking place inside the reactor, then I can write R is equal to K C, that is it. I have not used the subscript A because we are following only the concentration of A. So, Kca or Kc in this particular case is the expression for rate of reaction. Now, having known this, I have now analyzed what is going on as a flow process and as a reaction in the reactor. Now, what you can have is a situation where the reaction is exothermic, meaning that some amount of energy would be liberated by, or heat would be liberated by the system, and if you want to maintain a constant temperature T, then you will have to take that heat out of the system. So, therefore, this particular arrangement is also called diabatic operation of the reactor. Diabatic operation of the reactor means that exchange of heat is allowed in the system. So, what can be a possible arrangement in which you would be in a position to take out the heat from the system? I will put a jacket around my reactor. So, let us say that I have a jacket and there would be a stream of the cooling fluid which would be going continuously in and it would be coming continuously out. Okay. So, again the volumetric flow rate of the cooling fluid can be denoted as F J in volumetric flow rate of the jacket fluid or the cooling fluid inlet, and F J out. Okay. And temperature T can be denoted as T j in the jacket the temperature of the jacket fluid at the inlet and the temperature of the jacket fluid at the outlet. Nothing more than this specification is required. Okay. Now, this is the most general synthesis of the process, the adiabatic transient operation of a CSTR, which has been presented in front of you. To obtain the model equations which have been shown on the left hand side and certain quantities which are different from what has been drawn on the right hand side than what has been shown on the left hand side, we need to carefully look at the assumptions. Okay. So, the overall picture is this, that what you can see on the right hand side is that there is an irreversible first order reaction A going to B, which is taking place in a CSTR. The inlet flow rate is F in volumetric flow rate. The concentration of the species A is in the feed is Cf, it comes at temperature Tf, F stands for feed. There is a well mixed system inside the reactor. So, there are no temperature or concentration gradients, spatial gradients inside the reactor. So, therefore, concentration of A inside the reactor is C, temperature is T, the volume is V. At this point of time, we do not know or we cannot say whether the volume V of the reaction mixture is a constant or a variable. We have just denoted it as V. The rate of reaction is R. And then, since this is the case that you have well mixed case, at the outlet you have the concentration of the species is simply C, which is same as that in the inside the reactor, and temperature T, which is same as that inside the reactor. The volumetric flow rate would be F out. At this point of time, we do not know the relationship or inequality which exists between F in and F out. Similarly, to maintain a constant temperature, to take out the heat of reaction for the case of exothermic reaction, to supply also equivalently the heat to the system for an endothermic reaction, you generally will not have a jacketed system, you will have a coiled system, but in either case to have the energy exchange for a diabatic operation, you have the flow rate of the fluid in the jacket given as F j in and outward flow rate, outlet flow rate as F j out, J stands for jacket. Similarly, you have temperature at the inlet as T j in and temperature at the outlet as T j out. This is the entire description of the system. Now, we will make certain approximations, we will make certain assumptions to reduce all of these quantities which have been shown on the right hand side to conform to the equations which have been given on the left hand side. So, let us see what those approximations are. So, the first thing which I can do is I can write a mass balance over the system. Okay. So, I have simply a tank. Okay. So, this is my tank in which material is coming in, material is going out, certain level is maintained. This is the classic example of a liquid level system which we have been studying right from the first day. Remember our equation that there used to be d h by dt is equal to 1 over A q 1 minus q 2, right. That used to be our mass balance equation with q 1 as the inlet flow rate and q 2 as the outlet flow rate. So, for the overall mass balance it is the same case, you have the rate of change of mass inside the system given as d by dt of mass is given as rho times volume. Remember when we solved this particular case previously, we had assumed constant density and density got cancelled out from both the sides. Now, we are explicitly taking the density in this case and this would be equal to what? if there occurs a change in the density of the system, which means that the density in the inlet is something different and density at the outlet is something different, then the volumetric flow rate F in multiplied by the density at the inlet would give you the mass flow rate in, and similarly minus F out, and the density of the reaction mixture has been assumed to be rho. So, this would be simply rho. So, F in rho, this would be rho, this would be F out rho, right. Now, under an approximation that you have constant density, the density does not change. Okay. Well, anyway you would not expect a temporal change in the density of the system, but there may be temporal variation in the temperature of the system, and with changes in the temperature of the system the density may change, and that is how temporal variation of the density may happen, as well as spatial variation may happen when you compare the density at the inlet and density at the outlet. When you assume that this does not happen, which means that you have a constant density, that then under such a case I can simply write d V by dt is equal to F in minus F out. Okay. So, the first thing you will see that in your original equations there were no densities, and now you see that we have gotten rid of density because we have assumed that the density does not change. This is an approximation, and we must remember that we have made this approximation. So, subsequent analysis would be true as long as this approximation holds true. Now, we have this first equation, which is d V by dt is equal to F in minus F out. Now, imagine that you do an operation in which you will maintain the liquid level. Okay. So, under such assumption, the volume, the overall reaction volume or the volume of the reaction mixture remains constant, right. So, you have inlet flow rate, you have outlet flow rate, and the liquid level in the tank in the CSTR remains constant, which means the volume of the reaction mixture remains constant, in which case I can write F in is equal to F out, which means constant volume. And when F in is equal to F out, which means the total mass which is coming in is equal to the total mass which is going out, then under that condition I can simply write F in is equal to F out is equal to F, and that is the F which you see in the diagram on the left hand side. The volumetric flow rate, you are assuming that the operation is taking place at a steady state. So, there is no change in the volume of the system, and therefore, the inlet flow rate is equal to the outlet flow rate. Fine. So, this was the overall mass balance. What now we can do further is do a component balance. So, this was the overall mass balance. It is the result of overall mass balance that we got an idea that the inlet flow rate would be equal to the outlet flow rate. So, therefore, we have changed F in and F out to simply one quantity F, which is the volumetric flow rate of the quantities which are flowing through the system. Now, we can do a component balance. How does the variation of the reactants or the products take place in the system? We will do only one, because the other one can be obtained pretty trivially. So, now I can do the component balance. If C is the concentration, so then the amount of A inside the reactor its temporal variation would be given by d by dt of concentration multiplied by volume, the reaction mixture volume, and V has been assumed to be constant from the previous assumption. So, therefore, I can simply write here, I can take V out, but at this stage I am writing this as d by dt of C multiplied by V. Now, sum of the A would be coming in, inside the reactor there would be reaction, and the unreacted A would flow out. So, I have three processes going on: change in the concentration because from the inlet stream A is coming in, change in the concentration because from the outlet stream A is going out, and within the reactor change is taking place anyway because of the reaction. So, let us see what will happen. I have flow rate F in multiplied by the concentration or the amount which is coming in the feed. So, concentration in the feed. So, this is C f minus the analogous quantity in the outlet. So, F out C, because I know that whatever is present in the reactor is going out. So, the concentration of A in the outlet stream would be simply C minus R times V. Okay. So, R is the rate of reaction which would be expressed per unit volume. So, when you multiply it with volume, you will get the time rate of change of the concentration of A in the reactor because of the reaction. Now, we have assumed that F in is equal to F out, which is equal to F. Okay. F in is equal to F out, which is equal to F, and therefore, from here and volume is constant. So, I can write this as V d C by dt is equal to F C f minus C minus R times V. In other words, d C by dt is equal to F by V C f minus C minus R. This is the equation which we get from component balance. So, by looking at the figure which is on the left hand side, I now am in a position to appreciate that why I have F here and F here instead of F in and F out, why I have C f, and I cannot say anything about T f just by the mass balance. So, let me not put any arrow here. I have why I have C here, which is the same C here, okay, and why I have a V here, and why I have an R here. Okay. So, using mass balance and using component balance, I could get this particular equation, which is our working dynamical equation, one of the working dynamical equations. The second dynamical equation involved temperature, and to have an idea about temperature, we need to do energy balance. So, let us look into the energy balance. So, now I have a system in which I have the variation of temperature, a possible variation of temperature, and heat exchange is allowed, it is a diabatic process. So, therefore, MCPT, if MCPT is the energy content of your system, then I can write d by dt of m. M is given as volume times rho, Cp times T is the change in energy of the system. Now, change in mass of the system was given as d by dt of V times rho. Change in a particular component was given by as d by dt of volume times the concentration. So, similarly, I am writing an analogous expression here, and this would be equal to the inlet energy minus outlet energy. So, energy change due to flow, right. So, my flow rate from the previous analysis was F in rho in Cp T F, the feed temperature, okay, minus, because of the flow I can write F out rho was the concentration, was the density in the reaction mixture, and that is the same density which is going out. So, rho Cp T, T is the temperature at which the reaction mixture is there, and that is the temperature at which the stream leaves. Plus, now there would occur an energy change in the system because of the reaction. The reaction can be either endothermic or exothermic. So, if the reaction is exothermic, energy would be added to the system. If the reaction is endothermic, the energy would be extracted by the system, and therefore, depending upon that you will have either positive or negative sign for delta H. So, minus delta H if the reaction is expressed in terms of as per unit volume, then V multiplied by R, where R is the rate of reaction. So, this is the energy change because of the reaction. Now, you have a jacket, and across the jacket you have the energy change. Okay. So, therefore, this is given as U minus U A T minus T j. Now, this is an important assumption which we need to remember. Okay. So, now what you have is a system in which the jacket has well mixed contents. So, the jacket is well mixed, which means that there will not be any gradients, spatial gradients within the jacket. Okay. In other words, I can write T jacket in, which I had written in the previous analysis, would be equal to T jacket out, and this has been simply represented by T j. Okay. Let me say it again, that the contents of the jacket have been assumed to be perfectly mixed, which means that there will not be any spatial gradients of temperature of the jacket fluid inside the jacket, and therefore, T j in has been assumed to be equal to T j out, which should be equal to, which has been now denoted as T j. Okay. What else do you assume? You have assumed constant density. So, rho is equal to rho in as a constant. This you have established in the previous balance. V is a constant, and now what you are also assuming is that the material properties are constants, which means that specific heat, we know that specific heat can be a function of temperature, but for this analysis you have assumed that Cp is a constant. Okay. And also F in is equal to F out is equal to F. If this is the case, then you simply write this as V times rho times Cp dt by dt is equal to F rho Cp T feed minus F rho Cp temperature of the reaction mixture plus minus of delta H volume times R minus UA T minus T jacket. This becomes your balance equation. So, this is the energy balance. Now, certain assumptions further in this case, or observations rather, you have minus UAT minus TJ. This basically means that you have the flow of heat from the system, from the reaction mixture to the jacket fluid. Okay. So, which in turn means that you must be having an exothermic reaction, and if the reaction is exothermic, then you see that the term which involves the energy contribution or energy change from the reaction has a minus delta H, which means that you have the energy addition because of the generation of energy from the because of the reaction, and that energy is taken away by the jacket fluid. So, these are the again observations which you should make for this particular equation. So, by the overall mass balance, component balance and the energy balance, you can see that these are the two equations which you have in front of you, and these are your dynamical equations. So, your dynamical variable in the present case will become C, the concentration of A inside the reactor, and temperature, the temperature of the reaction mixture in the reactor. You have two equations, both are first order. So, I have two first order ODEs, which means I have a second order system. Now, everything which we studied about second order dynamics should now come in front of you, that what all can happen to this particular system. Further, one more thing which you can write about this is that this is a non-linear system. Okay. So, if possible, you could solve this non-linear system directly and get the temporal variation of concentration and temperature with time. If not, then you would tend to linearize the system and analyze the linear dynamics, or in other words, you would determine the steady state concentration and temperature in the system. About this steady state, you will analyze the dynamics of the system by doing the linearization of the equations which we developed. So, what we will do is we will stop here today, and in the next lecture we will continue this discussion and try to understand the dynamical features as well as the steady state features of the system. Thank you.